We made reaching out to the school and the wider community an emphasis from day one. We launched our website just before the start of the UK competition, which contains relevant information about the CANSAT. And we also have a Twitter feed, which has been a constant source of entertainment for all our followers, especially during the more hair-raising moments of the competition.
We presented to the school's Engineering Society and SPS Space, which concerns itself mainly with other high-altitude balloon projects. Since then, we've been presented with the UK trophy at a whole school assembly, and this has significantly raised the profile of SPS Space. And before the competition begins in earnest, we hope to do more assemblies to other year groups.
I'm in charge on the mechanical side of this design, which for a rover, I think you'd agree, is critical. Our aim in this CANSAT project is to keep things simple. You can see this with our parachute release, which is essentially just 2 copper plates and a bar, and especially with our strut release, actually integrated into the wheel. The idea is, the less things there are on the CANSAT, fewer things can go wrong.
The chassis we designed for the UK competition ended up being far too light, falling well short of the 370 grams stipulated. As a result, we had to add a surprising quantity of lead weights.
I was in charge of the electronics design for the project, which was a fiddly little task because there were many very small components, the smallest of which had a pin spacing of just 0.3 millimeters. But we decided in the end to use a separate breakout for the microprocessor, which let us use a far more powerful chip than we would have been able to solder by hand. And in the end, we managed to get, I think, really quite a good set of electronics. Now, I would say the electronics are definitely a strong point of the CANSAT, with a processor with a phenomenal clock speed of 96 megahertz and a whopping 64 kilobytes of RAM.
The electronics have the advantage of measuring temperature both inside and outside the can, which means we can get a good idea of the air temperature, but also the temperature of the electronics inside the can.
These things aside, our strongest point is probably being able to learn from our mistakes.
That means we've been doing really quite a lot of learning.
The CANSAT, although it worked quite well, suffered from several serious flaws. On landing during the UK finals, there were several issues. The parachute failed to deploy properly for a start.
For the European finals, we hope to strengthen the wheel bearings using a Lazy Susan joint directly connected to the chassis and the innermost wheel.
The other issue with the rover in the UK CANSAT competition is that it struggled on long grass because it had too little grip.
Because the effective diameter of the wheels was so small, it also wasn't brilliant with large obstacles.
For the European finals, we're implementing one of 2 possible systems to make the diameter of the wheels larger, while still fitting inside the form factor of a drinks can.
There was one last issue, which was team availability. We found it to be really quite difficult to get everybody together for one meeting, and as a result we had to resort to Skype meetings and smaller groups. Fortunately, though, everybody was experienced enough in the workshop that, although we had restricted hours in there, we were able to get the project completed in time for the UK final.